Hello, my name is Kelsey Lowrey, and my presentation explores spatial reasoning and attitude among undergraduate females in STEM versus non-STEM fields. The Spatial Intelligence and Learning Center defines spatial reasoning as the ability to rationally envision the relationship between positions, shapes, objects, and directions in 2- and 3-dimensional spaces. Spatial ability can be divided into specific categories, such as mental rotations, mental cutting, mental folding, and general spatial awareness. On the right, with the square and cylinder, we can see examples of the types of questions asked in assessments of spatial reasoning in 2- and 3-dimensional spaces. Examples of some types of questions asked in 2-dimensional settings found in the square include shape matching after rotations and combining shapes by rotating or fitting together smaller components to make a bigger shape. Examples of some types of questions asked in 3-dimensional settings found in the cylinder include aerial views of what a 3-dimensional object would look like from a top view, what shape is formed from a planar cut, and being able to identify the resultant cube built from folding 2-dimensional squares. There are broad applications of spatial reasoning in mathematics and science, such as working with span and vector spaces in linear algebra, vector addition and sketching problems involving gravity in physics, and protein structure and folding and 3-dimensional cell models in biology. Earlier results have illustrated that spatial reasoning is a major contributing factor in developing proficiency and future achievement in STEM. It is unclear how choice of a STEM or non-STEM major and personal attitude affects spatial reasoning ability in females. There is uncertainty in what determines female spatial reasoning ability, since no research has been conducted solely focusing on female spatial ability. Past research efforts have focused on the differences in male versus female spatial ability. Most research has confirmed that males typically outperform females in spatial reasoning ability, especially in the context of mental cutting. As we can see in the graphic on the right, males also hold more STEM jobs than females. Poor spatial skills in the female population may be hindering their success in the STEM field. Their poor performance could account for their underrepresentation within STEM. Hence, this begs the question as to why are females performing poorly in spatial reasoning and what is hindering their success. Therefore, in my study, I wanted to explore the differences in female spatial reasoning performance between STEM and non-STEM females. So general information about my sample population is shown here. So my sample was comprised of the undergraduate female population from Fresno Pacific University. There were 34 STEM and 32 non-STEM females surveyed from a diverse group of 18 to 22-year-olds. For research purposes, this was a voluntary single-blind procedure. The design of my study included a spatial reasoning assessment and a personal survey. The spatial reasoning assessment measures spatial reasoning ability with a quantitative assessment. It was 14 multiple choice questions, testing the subject's ability on mental cutting, rotations, folding, and general spatial awareness. Questions were pulled from well-known spatial reasoning test resources of the Purdue Visualization of Rotation Test and Barron's Mechanical Aptitude and Spatial Relations Test. And based on if subjects answered questions correctly or wrong, I recorded total scores and subsection scores. The personal survey qualitatively measured personal attitude and external influence. In my study, personal attitude refers to one's viewpoints and beliefs towards STEM and spatial reasoning. External influence is defined as influences from parents, teachers, and learning environment. Questions in the personal survey were free response, asking about demographics, major, personal attitude, and external influence of the participant. Questions ask participants to describe or rate what influenced them to pursue or not pursue the STEM field. They were also asked if they were influenced by family, teachers, or their own abilities in their educational pursuits. I then implemented a systematic scoring scheme, adding the values of the two categories of personal attitude and external influence in order to score the personal survey. In my data analysis, I used a paired two-tailed t-test to analyze the spatial assessment scores, as this is a simple test that compares two averages and if their difference is due to chance or not. I then used a correlation coefficient to analyze my personal survey scores, as the coefficient is a statistical measure of the strength of a linear relationship between two variables. So these are some of the examples of questions from my spatial reasoning assessment and personal survey. So as you can see here in number 8, this is a question about finding rotated shapes. So you have a shape on the left and it's rotated a certain degree to the right, and you have to find the shape on the right that matches it. And then number 2 is the mental cutting shapes and trying to find the correct shape when you have the 3D object. It's cut with a plane, and then you're trying to find the object on the right that matches the two-dimensional shape when you look on top. And then for the personal survey, the first question, number 6, asked participants what influenced them to pursue a STEM field, and the second question, which is number 7, asked them what influenced them to not pursue a STEM field. But both questions asked if they would attribute this to family influences, support from teachers, or their own abilities, and also if they were encouraged or discouraged from pursuing STEM. So in my first figure, averages were calculated for total and subsection scores between STEM and non-STEM females. So figure 1A shows total score averages in STEM and non-STEM females. And we can see here that the total score averages between these two populations is not statistically significant, with our p-value being greater than 0.05. Our figure 1B shows subsection score averages in female STEM and non-STEM populations. No subsection score average between the two populations were statistically significant, with our p-value for each section also being greater than 0.05. Although we can observe trending behavior, as the mean for total assessment score in STEM females is a whole point higher, and subsection scores for STEM females are also higher in the averages in all 4 categories. And also figure 2 looks at how the participants' attitude and influence affects their spatial score. So each subject was categorized based on their personal survey score. If they had positive influences towards STEM and spatial reasoning, they were given a score between 15 and 20, which was labeled as good. And then if they had a negative influence, they were labeled as satisfactory and poor, with scores labeled here, as you can see. And so the total assessment score of STEM and non-STEM females is represented as a function of their personal attitude and external influence score. If total assessment score spatial reasoning ability is dependent on the participant's attitude and influence, we would expect a positive linear relationship. Therefore, we would expect that poor and satisfactory participants would yield lower spatial reasoning scores, with a strong linear relationship with our R coefficient closer to 1. And we would also expect participants labeled as good to yield higher spatial reasoning scores and have a strong positive linear relationship. For example, as we could see in the figure, non-STEM good and satisfactory influence scores, represented by the light green and the navy blue dots, we observe a weak positive linear relationship with our R values of 0.34 and 0.29. We can observe that the STEM good category, which is labeled as the yellow squares, is clustered in the top right corner which is a higher total assessment score. However, generally, there is a lack of strong positive linear relationship between spatial assessment score and attitude and influence for STEM and non-STEM females. Overall, there were no statistically significant differences in spatial reasoning ability between the two populations. Although none of the data is statistically significant, we are confident that the trends from the data would uphold with greater sample size. It may also be interesting to focus on how first-generational status affects spatial reasoning ability. From this study, we have seen that attitude, nor influence, nor major explains female poor spatial reasoning skills. A question you may still have is, what does this study have to do with female underrepresentation in STEM? We are proposing that poor performance in spatial reasoning may be responsible for underrepresentation in the field. This leads us to explore in this study why females are underperforming in spatial reasoning abilities. Perhaps spatial reasoning is the cause of the lack of numbers of females involved in STEM. Therefore, it is worth further researching the intricacies involved in female spatial reasoning ability in future studies. Okay, thank you for your time and consideration.